previous lecture, we introduced the objective and the approach of the material requirement planning tool to the task of materials planning. Moreover, we discuss in detail the procedure and we get some practice through one application example. Thanks to this, we get more acquainted with the advantages of this method, which is the synchronization of production and supply, especially in very complex production environments with variable demand. Of course, through the example, we started to understand also MRP limitation, to which this lecture is devoted. According to Orlicki, the father of MRP, the MRP procedure has some critical system design features that, for the sake of brevity, can be synthesized into just two. The first one is the large amount of data needed, which is then connected with one feature of the MRP, which is its nervousness or instability, and the assumption of infinite capacity, which is also connected to the use of fixed lead time as an input to the procedure. Let's start from the first problem. As we saw through the example, a lot of data are needed to run the procedure. This data may be coming from the technical domain as well from the managerial domain, and this data can be just used and read throughout the procedure or can be also updated throughout the procedure. All this data, such as the bill of material, the production lead time, the lot sizing policy, the safety stock, the inventory position, and the orders in progress, just to name a few, they have to be correct and they have to be updated so as to avoid the garbage in, garbage out problem. In fact, if these data are not accurate, the results of the proposed orders will not be useful in terms of synchronization of production. But there's also another very important feature connected with the MRP procedure, which is its own instability. If we also apply small changes in the input data, the result from the MRP elaboration will be a large variation in the proposed materials plan. This subject has been studied a lot since the very emblematic paper of Mather in 1977, whose title was "Reschedule the reschedules you just reschedule." And notwithstanding with this problem, complex management decisions they have to be taken in order to deal with this. For instance, MRP run frequency and frozen periods, they have to be defined also taking into account the MRP nervousness issues. Also connected with data management, we have to consider all those management decisions that will produce data to be used in the MRP procedure. One example is the safety stock data. In this regard, safety stock positioning as well as reordering policy, they have to be defined and they have to be correct and updated so as the procedure to work properly. The second problem is connected with the infinite capacity assumption. In fact, during the MRP procedure, production capacity limits can be violated because multiple orders can be loaded into the same period of time, and the procedure is not capable of managing this. The only optimization of production capacity is done through the use of specific lot sizing rules, but it's a very indirect optimization. Also resorting to the capacity requirement planning features of the MRP2 family softwares, these problems can be just mitigated. In fact, we can start from an initial situation in which production capacity constraints are violated, and through an iterative process done by the human planner, we can get a solution which is more feasible from the production capacity point of view. A complete automation of this task is still nowadays not possible, not only for technical reasons and for computational complexity reasons, but also for the very important managerial implication connected to the decision of which item to keep in delay. Still connected with the topic of infinite capacity is the assumption of fixed production lead time. As we know, the more the workload in a production system is increased, the longer the lead time will be. Therefore, production lead time should be not considered as an input to the production plan, rather as an output of the production plan, since they strongly depend on the actual workload on a given resource on a given period. In this way, when we use a fixed lead time value, therefore because we assume an average workload situation in a given period, we may be making big mistakes. For instance, if the actual workload is higher, then the lead time will be longer and the components will not be delivered on time. Or conversely, If the workload is lower, then the lead time will be shorter and extra inventories will be generated, which is in contrast with the objective of the MRP procedure. This is also connected to the topic of the planning horizon. In order to avoid plan unfeasibility, as we know, the planning horizon has to be longer than the sum of all the manufacturing and purchasing lead time of all the items in the bill of material. Therefore, again, if we underestimate lead times, this may lead to stock out of components, and therefore this may leave the entire rendezvous policy in tatters. On the contrary, if we overestimate lead times, this may lead to an expansion of the planning horizon, which implies two big problems. On the one hand, again, we have the risk of excessive stockholding cost, and on the other hand, we will have a risk for lower data reliability, since the longer the lead time and the longer the planning horizon, the more forecast data will be used into the planning procedure, and therefore more changes in the future run of the MRP will be given, this leading again to MRP nervousness. In a nutshell, the MRP has been very important historically to help companies to successfully deal with the materials planning task in an increasingly complex environment with complex products and variable demand. But the simplicity of its procedure, so the sum and split and shift procedure, actually hides some relevant design criticalities which have to be deeply understood in its application. Actually, the latest advancement in technologies such as Internet of Things devices to have some real-time monitoring of inventories, of integrated IT systems, or the increasingly available computational power may be mitigating some of these criticalities, which nevertheless still remain relevant in most large-scale real-life applications.